First, here is the big idea. Uniform circular motion means an object moves around a circle at a constant speed, but its direction changes every instant. And because velocity includes direction, the velocity is changing even when the speed is not. That is why circular motion is never truly acceleration-free. Throughout this short lesson, we will connect the shape of the path, the direction of velocity, and the inward acceleration, called centripetal acceleration. The key idea is simple but subtle. In uniform circular motion, the object keeps the same speed while traveling along a circular path. Examples include the hands of a clock, a propeller spinning steadily, a satellite orbiting Earth, or a car moving around a circular track at steady speed. At every point, the velocity points tangent to the circle, not toward the center. So even though the speed stays fixed, the changing direction makes the velocity continuously change. Next, why is there acceleration at all? Because acceleration is the rate of change of velocity, and here, velocity changes direction continuously. The acceleration is called centripetal acceleration, and it always points toward the center of the circle, perpendicular to the velocity. Its magnitude is a sub c equals v squared over r. So what does that mean? Higher speed makes the inward acceleration grow quickly, and a smaller radius makes the turn sharper and the acceleration larger. If we describe the motion mathematically, the position vector can be written as r of t equals a cosine omega t in the I direction plus a sine omega t in the j direction. Differentiate once, and the velocity becomes minus a omega sine omega t I plus a omega cosine omega t j. Differentiate again, and the acceleration is minus a omega squared cosine omega t I minus a omega squared sine omega t j, or simply minus omega squared times r. Also, one full revolution has period t equals 2 pi over omega, which is also 2 pi r over v. Zephyr acceleration requires a net force, so uniform circular motion also needs an inward net force, called centripetal force, with magnitude F equals mv squared over r. But this is not a brand new force of nature. It is a role played by real forces, such as gravity, tension, friction, or the normal force. A satellite can be held by gravity, a ball on a string by tension, and a turning car by friction. The possible accelerations span an enormous range, from Earth around the Sun at about 5.93 times 10 to the minus third meters per second squared, to the edge of a CD at 5.75, to an electron in a simple Bohr model at about 9.0 times 10 to the 22. Here is a concrete example. Suppose a jet flies at 134.1 meters per second, and the pilot experiences a centripetal acceleration of 1g, or 9.8 meters per second squared. Using r equals v squared over a, the turning radius comes out to 1,835 meters, which is 1.835 kilometers. The implication is important. To create a larger centripetal acceleration, the jet must either move faster, turn with a smaller radius, or both. Fast motion and tight curvature together create the strongest turn. Zephyr. Finally, circular motion is not always uniform. If the speed changes as the object moves around the circle, then there is also tangential acceleration, a sub t, along the direction of motion. The total linear acceleration becomes the vector sum of centripetal and tangential parts, and those two components are perpendicular. In one worked example with radius 2.0 meters and speed v of t equals 4.0 minus 6.0 over t squared, the speed at 2.0 seconds is 2.5 meters per second. The centripetal acceleration is 3.1 meters per second squared, the tangential acceleration is 1.5, and the total is 3.44 meters per second squared at 64 degrees from the tangent. That is the difference between constant turning and turning while also speeding up or slowing down.